Walk into any massive data center today, and you will see absolute uniformity. Whether those servers are stamped with the logo of Dell, HP, or Lenovo, they all process information using the exact same identical silicon foundation. The Silicon Tribe won the hardware war decades ago, establishing a universal standard for how a computer works. Walk into a quantum lab today, and you are stepping into a zoo. There is no standard quantum computer. There is no Intel Inside. Instead, you will find wildly different, physically bizarre machines that look nothing like each other, built by competing groups of physicists who completely disagree on how a computer should be constructed. The cause of this chaos is the qubit. A qubit is the basic unit of quantum information, capable of existing in multiple states at once through a property called superposition. To use it, researchers must physically manifest this mathematical probability in the real world. Engineering a physical object that can hold a quantum state without collapsing is a massive, unprecedented technical hurdle. Because of that difficulty, the world's leading technology companies have fractured into separate factions. Each group is placing financial bets on completely different physical materials to act as their qubit. These machines can simulate molecules and optimize global networks in days rather than years. Because these capabilities would grant a permanent lead in drug development and national security, the faction that scales their chosen qubit first secures a monopoly on 21st century infrastructure. This table breaks down the strategy of the Superconductors, a faction led by companies like IBM and Google. They build artificial atoms out of superconducting metal loops. These loops operate at nanosecond gate speeds, but they require dilution refrigerators, massive, energy-hungry devices designed to freeze the chips to temperatures colder than deep space. Competing against them is the trapped ions faction. Companies like Quantinium don't build artificial atoms, they use the real thing. They levitate individual charged atoms inside metallic vacuum chambers, manipulating them with lasers. They sacrifice operation speed for high fidelity, which measures how closely a quantum operation matches its intended outcome. Then you have the light chasers, who encode qubits into particles of light to run computations at room temperature. Meanwhile, the Silicon Spin Tribe, led by Intel, is trying to trap single electrons inside standard silicon transistors, hoping to retrofit existing microchip factories to mass-produce qubits. Every faction is trapped in an engineering deadlock. Superconductors are fast but delicate. Trapped ions, accurate but won't scale. Photonics, room temperature but lose data. Speed, fidelity, and scale pull in opposite directions, and physics refuses to grant all three at once. This diagram compares the three distinct structural paths for quantum computing architectures. Beyond physical materials, there is a deep division over how the system processes information. The left column shows gate-based systems, which execute sequential logic operations and act as universal orchestrators. In the middle, you see quantum annealing. These are narrow optimization specialists that settle qubits into the lowest energy state of a defined landscape. On the right is the topological approach. Pursued by Microsoft, this architecture physically braids the paths of particles to create a knot, an approach companies are already using today to optimize complex logistics routing. This structure protects the quantum information from environmental noise without requiring layers of extra hardware. Universal logic, optimization landscapes, and topological knots solve different classes of mathematical problems. The ultimate victor may not be a single architecture, but a hybrid federation where different machines are networked together to handle specialized tasks. Raw qubit counts are often used as a marketing tool, but they hide a massive engineering hurdle: decoherence. Decoherence is the process where a particle loses its quantum state the moment a stray vibration or temperature fluctuation touches it. To perform long, complex calculations, engineers rely on error correction. They group hundreds of unstable physical qubits together to act as one single logical qubit. A logical qubit is a stable, virtual unit designed to detect and fix errors automatically, so the calculation can continue. The race is no longer about cramming more noisy parts onto a chip. The moment a company scales a reliable logical qubit, quantum computing moves from a delicate physics experiment into a commercially ready product. Because these logical qubits require extreme physical environments to survive, the resulting hardware is exceptionally heavy. These are installations that depend on massive vacuum chambers, elaborate cryogenic cooling pipes, and specialized power grids. We are seeing a return to the spatial reality of the 1940s. Just as the earliest computers filled entire rooms, the quantum cloud will not be decentralized or mobile. Access will be distributed globally, but the physical machines will be anchored to specific, heavily guarded zip codes. You cannot smuggle a dilution refrigerator across a border in a backpack. You cannot easily migrate its physical state to a backup server in another country. The physical location of a functional quantum computer instantly becomes a national vulnerability and a point of geopolitical leverage. Governments are heavily subsidizing this hardware. The United States, China, and a federation of European nations are pouring billions of dollars into domestic quantum hubs. They are building sovereign capacity to ensure their intelligence agencies and financial sectors never have to rely on a foreign adversary's machine. Breaking modern encryption would grant access to decades of stored diplomatic and financial data. This risk drives the harvest now, decrypt later strategy, where adversaries collect encrypted data today to unlock it the moment a functional machine exists. Beyond security, a stable machine grants an insurmountable advantage in simulating chemistry for drug discovery, designing zero-loss energy materials, and accelerating artificial intelligence. The quantum hardware war is a race to build the platform that handles the world's most complex problems. The winner will control the digital infrastructure that secures science, security, and global finance for decades.